Hello, good evening. We're going to look at Chapter 15, Aromaticity, Reactions of Benzene. So we're going to define aromaticity and get into some of the reactions of benzene in this chapter. Benzene is found in many different products, including jet fuels. And aromatic compounds are of health concern due to leukemia occurrence that has been noted in years past. Which compounds do benzene resemble, you may ask? Alkenes, dienes, of course, because both of those have double bonds. They are all nucleophiles, but benzene's aromaticity causes it to react in ways different from the reactions of alkenes and dienes. Benzene was first isolated in 1825 by Michael Faraday, who extracted it from a liquid residue obtained after heating whale oil under pressure to produce a gas for illuminating buildings in London. It was first called benzine, B-E-N-Z-I-N, and then later was called benzene. Benzene has relatively few hydrocarbons in relation to the number of carbons. Of course, there's 6 carbons and there's 6 hydrogens, so it's a 1-to-1 ratio. Compounds like benzene have been found in oils from various trees and plants, and chemists call these compounds aromatic because of very pleasing fragrances. They're different from aliphatic compounds with higher hydrogen to carbon ratios, which came from fats. An aliphatic is a term that's usually implied for a non-aromatic organic compound, usually non-cyclic, like an alkane. Of course, in alkanes, if there are 4 carbons, there are 10 hydrogens. So the ratio is different in the hydrogen-carbon ratio with an aliphatic compound. So let's go to the next slide here. Criteria for aromaticity. This is a key point in our discussion of benzene. As you can see on the slide, a compound must have uninterrupted cyclic cloud of pi electrons above and below the plane of the molecule. That is one of the criteria that must be met for aromaticity to exist. Second, the pi cloud must contain an odd number of pairs of pi electrons. So you might want to think of benzene as a prototype for aromaticity. Benzene is planar. It's a cyclic compound with a cyclic cloud of delocalized electrons above and below the plane of the ring, as you can see here, and displayed in A and B. Due to the delocalized electrons, all the carbon-carbon bonds have the same length, somewhere between the length of a single and the length of a double bond. It is a very stable molecule due to its large resonance energy, and when a compound has an unusually large resonance energy, it is called aromatic. What structural features do aromatic compounds have in common? Compound must meet both of these structural features. For the pi cloud to be cyclic, the molecule has to be cyclic. For the pi cloud to be uninterrupted, every atom in the ring must have a pi orbital. That's shown in A in the slide here. And each p orbital must overlap with the p orbitals on the other side of it, above and below the plane of the benzene ring. And of course that's displayed in B. So the molecule must be planar. We know that the pi cloud of benzene contains 3 pairs of pi electrons, which is an odd number. And also C in our slide here, the electrostatic potential map for benzene shows that all of the carbon-carbon bonds have the same electron density. And you can see how the color is distributed across the molecule model. So let's look at Huckel's rule. Erich Huckel recognized that an aromatic compound must have an odd number of pairs of pi electrons. He stated it in the rule that you can see on this slide. For a planar cyclic compound to be aromatic, its uninterrupted pi cloud must contain 4n plus 2 pi electrons, where n is any whole number. So how many electrons must an aromatic compound contain? As it turns out, if n is 0, then the number of electrons would be 4n plus 2, which would be 2, and we'd have one pair of electrons. If n were equal to 1, we'd have 6 electrons, 3 pairs. If n is 2, we'd have 10 electrons. In other words, 4 times 2 plus 2 is 10, which would be 5 pairs of electrons. If n is 3, the number of electrons is 14. There would be 7 electron pairs. If n were 4, the number of electrons would be 18, and the electron pairs would be 9, and so forth. So how many pairs of pi electrons does Huckel's rule require? It requires 1, 3, 5, 7, 9 pairs of pi electrons. Let's go to the next slide. Monocyclic, or just one ring hydrocarbons with alternating single and double bonds, are called annulenes. A prefix in brackets indicates the number of carbons in the ring. You can see 4. There's 4 carbons in that ring of cyclobutadiene. Now, why are cyclobutadiene and cyclooctatetraene not aromatic? It's because they have an even number of pairs of pi electrons. And also cyclooctatetraene is not aromatic because it is not planar, but it's tub-shaped. Both of these compounds are not as stable as aromatic compounds like benzene. So, cyclobutadiene is not aromatic. Benzene, of course, is aromatic. And cyclooctatetraene is not aromatic. Moving right along. Why is cyclopropene, here on the left, not aromatic? Because it does not have an uninterrupted ring of p orbital bearing atoms. One of its ring atoms is sp3 hybridized, and only sp2 and sp hybridized carbons have p orbitals. And you can see this one up here and that one there, on either side of the double bond is sp2, whereas this one down here is sp3 at the point where the arrow is pointing. Why is cyclopropenyl cation aromatic? The second one. It has an uninterrupted ring of p orbital bearing atoms, and the p, or the pi cloud, contains 1, which is an odd number, pair of delocalized pi electrons. All of the carbons in the ring are sp2, hybridized. This compound has resonance contributors and a resonance hybrid as shown in the slide. You can see them down here. Why is cyclopropenyl anion not aromatic? Because although it has an uninterrupted ring of p orbital bearing atoms, all carbons are sp2 hybridized, its pi cloud has 2, which is an even number, pairs of pi electrons. So, cyclopropene, non-aromatic, cyclopropenyl cation, aromatic, and cyclopropenyl anion is non-aromatic. Cyclopropene cation is aromatic. Going on to some other examples here. Why is cycloheptatriene not aromatic? Although it has 3 pairs of pi electrons, it does not have an uninterrupted ring of p orbital bearing atoms because one of the ring atoms is sp3 hybridized, as you can see marked here on the slide. Why is cyclopentadiene not aromatic? It has an even number of pairs of pi electrons. There are 2 pairs, 1, 2, and it does not have an uninterrupted ring of p orbital bearing atoms. It has an sp3 hybridized carbon, as noted. right here. So this is not aromatic, this is not aromatic. These compounds are aromatic. Why are they aromatic? Because naphthalene has 5 pairs of pi electrons. 1, 2, 3, 4, 5. Phenanthrene has 7 pairs. You can count them. And chrysene has 9 pairs of pi electrons, all an odd number. Okay. Aromatic heterocyclic compounds. A compound does not have to be a total hydrocarbon to be aromatic. So we have heteroatoms. A heteroatom is a ring atom that is not carbon. The most common heteroatoms found in heterocyclic compounds are nitrogen, oxygen, and sulfur. Why is pyridine aromatic? This here on the left. Because it has 6 ring atoms that are sp2, which means they each have a p orbital, and the molecule contains 3 pairs of pi electrons. 1, 2, 3. The lone pair of electrons on nitrogen, right here, are not pi electrons. Now all of these compounds are aromatic. They have an odd number of pairs of pi electrons. They're planar and they're cyclic compounds. But we need to remember that a lone pair of electrons outside the ring is not a pair of pi electrons. A lone pair of electrons outside the ring, when in the presence of a negative charge, is a pair of pi electrons. A lone pair of electrons inside the ring is a pair of pi electrons. So we need to remember that. And as you can see, a heterocyclic compound is a cyclic compound in which one or more of the ring atoms is an atom other than carbon. So we have 3 pairs of pi electrons in pyridine, 3 pairs in pyrrole, 3 in furan, and also 3 in thiophene. We have 1, 2, 3. 3 is the one inside the ring. These right outside the ring are not pi electrons. These are not pi electrons, the ones outside the ring and furan, but the ones inside are pi electrons. Also those inside pyrrole, pi electrons. So 1, 2, 3. 1, 2, 3. These electrons outside pyridine are not pi electrons. So let's look a little more at pyridine. Pyridine is aromatic. Each ring atom, including nitrogen, is sp2 hybridized, so it has a p orbital. The molecule contains 3 pairs of pi electrons. Here's a pair right here, these two. And then this one along with this one, and then this one along with this electron forms the 3 pairs of pi electrons. Why don't the electrons shown on nitrogen count? Because they are not pi electrons. They're outside the ring. Nitrogen is sp2 hybridized, so it has 3 sp2 orbitals and a p orbital. The p orbital is used for the pi bond. 2 of the sp2 orbitals overlap the sp2 orbitals of the adjacent carbon atoms, which are not shown, and the 3rd sp2 orbital contains the lone pair. The p orbital electrons form an uninterrupted pi cloud above and below the pyridine ring. Pyrrole is also aromatic, as you can see here in this slide. In the case of pyrrole, the electrons shown on nitrogen are pi electrons. The resonance contributors show that the nitrogen atom is sp2 hybridized, and it uses its 3 sp2 orbitals to bond to 2 carbons and 1 hydrogen. The lone pair of electrons are in a p orbital that overlaps p orbitals on the adjacent carbons, forming a pi bond. How many pairs of pi electrons does it have? 3. So it is aromatic. And furan is also aromatic. It's a stable aromatic compound. The oxygen in furan is sp2 hybridized, and one lone pair in an sp2 orbital. perpendicular to the p orbitals is present. The second lone pair is in a p orbital that overlaps the p orbitals of the adjacent carbons, forming a pi bond. So they are pi electrons. And of course this is nitrogen right here, and oxygen is over here, as you can see. Okay, I think we'll stop at this point and take a break. Thank you.